Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 5.19. The problem statement says, Sachs and Lewis describe the hazards of breathing air containing appreciable amounts of asphyxiant, a gas that has no specific toxicity but when inhaled excludes oxygen from the lungs. When the mole percent of the asphyxiant in the air reaches 50%, marked symptoms of distress appear, and at 75%, death occurs in a matter of minutes. A small storage room, whose dimensions are 2 meters by 1.5 meters by 3 meters, contains a number of expensive and dangerous chemicals. To prevent unauthorized entry, the room door is always locked and can be opened with a key from either side. A cylinder of liquid carbon dioxide is stored in the room. The valve on the cylinder is faulty, and some of the contents have escaped over the weekend. The room temperature is 25 degrees Celsius. Part A. If the concentration of CO2 reaches the lethal 75 mole percent level, what would be the mole percent of what would be the mole percent of oxygen? Okay, so let's look here. This is the situation. We've got a canister, gas canister. The valve on the pressure regulator is broken, and so some of the gas is leaked into the room. Okay, the temperature in the room is 25 degrees Celsius. The pressure is just atmospheric pressure. And that's the leaking tank. These are the dimensions of the room, so that'll tell us like the volume space that the room occupies. Okay, so these are important for calculations. We've got our pressure, our temperature. We're putting these into absolutes and SI units so that we can do all of our calculations and have the units agree in terms that we understand. And then we're putting the room into meters. The room volume, calculating what that is. Okay, so for part A, they said, what's the concentration, what would be the mole percent of oxygen if CO2 is at the lethal limit? Okay, so initially the room is full of air, and the mole fractions look like this. We're going to assume that. The final state of the room, we know we've got 75 mole percent carbon dioxide. We know that the air in that case would be 25% of the room, the remaining 25%. But we don't know exactly what the mole percent of oxygen is. Okay, so we know that this ratio that oxygen and nitrogen are in are going to be the same ratio here. Okay, so this 25% of air is going to have the same ratio of oxygen to nitrogen. Like, you're not going to end up with more nitrogen than you are oxygen, or more oxygen than you are nitrogen. It's still going to be in this ratio. Okay, so we use the same air ratios that we had before, or the same area ratios that we had before, and then we multiply that by the 25%, because we know that 25% is how much air is in there. Okay, so that's the oxygen ratio, and then that's the nitrogen ratio. If you add these up, they should equal 25%. And if you looked at these ratios, if you did like XO2 over XN2, you would get the same ratio as if you did XO1 over XN1. Those ratios are the same. Okay, so what's the mole percent? Well, you just turn this fraction into a percent, and that's the mole percent. Okay? So part B, how much CO2 is present, or how much CO2 in kilograms is present in the room when the lethal concentration is reached. Why would more than that amount have to escape from the cylinder for this concentration to be reached? Okay, so first we're going to look at how much in kilograms CO2 is in the room at the lethal limit. Okay, so this is our mole fraction. We want to know how many moles. Well, let's first off, how many moles are in the room? Well, we can figure out how many moles are in the room by using the ideal gas law, because we know the temperature and pressure in the room. Okay, so moles equals this using the ideal gas law. So we know that there are 368 moles in the room. How much of that is carbon dioxide? Well, 75% of the moles in there are carbon dioxide moles. Okay, so moles of carbon dioxide is equal to 276 moles of carbon dioxide. Well, how much mass of carbon dioxide is that? Well, the mass is related to the molar mass and the moles there. Okay, so we just multiply those together and we get that there are this many grams of carbon dioxide in the room, because I'm using grams per mole, and then we convert that into kilograms. So there are 12.1 kilograms. Okay, the follow-up question was, why would more than that amount have to escape the cylinder for this concentration to be reached? Well, let's think about it. So we've got this room here, right? And there's a bunch of CO2 coming out of the cylinder. Well, the room is not completely sealed, right? So we assumed that the pressure in the room was atmospheric pressure, right? So if the room was completely sealed and you had CO2 leaking into the room, then this pressure would go up, right? Because there's more pressure going into it from the gas cylinder. Well, that's not the case. The room isn't sealed, so there's the CO2 that comes into this room is displacing some of the air. Well, if you assume that the carbon dioxide and the air kind of mix together in here, and the room is not sealed, well, some of that carbon dioxide is going to leak out of the room over time, right? So you're not going to reach the lethal limit immediately, because some of that CO2 is going to leak out along with the air. It's only when the amount of CO2 that's leaking is greater than leaking out of the tank is greater than the amount of CO2 that's leaving the room, then you're going to start building concentration inside of this room, and then as that concentration builds over time, eventually you reach the lethal limit. So that's why more mass from the tank would have to leave the room. Okay, and this is another representation of that. So the room is not sealed, so you have a certain amount of air going in, and then you have a certain amount of air and CO2 leaving. Okay, so there's a third stream of CO2 going in here. So 3 streams are exchanging gas with the room volume. Stream 3, which is the out, passes some CO2 out of the room through diffusion. Okay. Part 3. Describe a set of events that could result in a fatality in the given situation. Suggest at least 2 measures that would reduce the hazards associated with storage of this seemingly harmless substance. Okay, so hazard, door locks from inside. Person needs a key to leave the room. Okay? What if somebody enters the room without a key? Well, that's a hazard, right? Somebody could enter that room, not have a key, and get stuck in the room. Have you ever left your house without your key? Well, it's probably really likely that you could enter a room without the key. Even if it takes the key to get it, what if you leave the key in the door? When you open the door, you accidentally leave the key in the door, you walk into the room, the door closes, your key's outside, you're inside, how do you get out? Right? You're stuck. Okay, that's one scenario. So a control for that is that the door is open from the inside. It cannot lock on the inside. You could always just use the handle and get out. Okay, so the room cannot be locked for occupants to the room. Another thing you could do is to prevent anybody from even entering the room. If they know that the oxygen level is low, you could put an oxygen detection system in the room. So there's a continuous sensor in the room that's sampling how much oxygen is in there. And if that oxygen level drops below the safe limit, then an alarm will sound, and then nobody's allowed to even enter the room. Okay? And if somebody's in the room when that goes off, then you just leave the room immediately. Like cause an evacuation until you can find out how to solve the problem. Okay. Now that is it for problem number 5.19. Thank you for watching, and I hope you found this video helpful on your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.